Hello students, so welcome to the lecture series on filter design. This is part 2 of the lecture series. We have already covered part 1 and there we have discussed IIR and FIR filters, their important properties and the expected questions that could be asked in GATE and the other competitive exams. So in this part we will start with method 1 of IIR filter design. IIR filter design. Okay. So this method 1 is actually called as design of IIR filters by approximation of derivative. Approximation of derivative. Okay. So this is the name. Okay. Okay. So let us first start with an analog filter is given. So an analog filter is given to us and it is defined by k equal to 0 to capital N AK. Okay. Now, as we know that differentiation of yt at t equal to nt, okay, at t equal to nt will be given as y nt minus y n minus 1 t divided by capital T. Now here t is actually, so we are actually sampling by t, so we are sampling by t. So here, so we have to convert this analog into digital now. So we will be sampling the signals. So here capital T is the sampling interval and if we sample yt then we get ynt, that is we replace t by n capital T. So small t variable is converted into n variable multiplied by capital T, where n variable is always an integer. Okay. So in this equation dyt over dt at t equal to nt. Now ynt is generally written as yn, okay, because this t is a constant. This t is a constant, that is actually the sampling interval. So this is the constant and here n is the variable. So what is the variable here? N is the variable, t is a constant. So that's why it is written as yn, where n is a variable and n is an integer only. So this can be written as yn minus 1 divided by capital T. Now we can see that the system function where yt is the input and output is d by dt of yt, then the system function is hs is equals to s, because the output is differentiation of the input. Thus the system is hs is equals to s, because if the input is ys then we know that the differentiation is written as s times of ys. So here hs is equals to s. Now similarly, if we look at the other side of the equation number, so let us say this is equation number 2. So when yn is the input, what should be hz? So that output is yn minus 1 divided by capital T. Now since we know that the input is yz and output is yz into, by taking the z transform of this, we can say that 1 minus z inverse divided by capital T. So hz will be equals to 1 minus z inverse divided by capital T. Now in this transformation, as we know that from equation number 2, this in time domain, that is dy by dt over t equals to nt, is equal to yn minus 1 divided by capital T. So the system functions in analog domain of this operation will be equal to the system function in discrete domain of this operation. So we can say that s is equals to 1 minus z inverse divided by capital T. Okay, so how we are getting this, let me explain you one more time. So this is the equation that we get, and in time domain, in continuous time domain, and this is the relationship between the continuous time domain equation and the discrete time domain equation. And then we actually try to convert the time domain, continuous time domain, into Laplace and discrete time domain into Z transform, and then we compare the two, that the systems doing the operation of differentiation in continuous time domain should be equal to the system doing this operation on the discrete time domain. So from there we are getting this. Okay, so the very important result is this, that whenever in any question we have to convert or we have to realize IIR filter using the derivative method, then S has to be replaced by 1 minus Z inverse divided by capital T. Okay, so S square will be equals to 1 minus Z inverse divided by capital T whole square. S to power I will be 1 minus Z inverse divided by capital T to power I. Okay, so if in any question we need to convert analog filter with transfer function h of as into digital filter using method of derivative, then simply h of z is equals to h of as, where s is equals to 1 minus z inverse upon capital T. Now let us do the mapping. Between S plane and Z plane. S plane and Z plane. Now, since S is equals to 1 minus Z inverse upon capital T, so we can say that Z is equals to 1 upon 1 minus S into T. Okay. Now, since S is equals to j omega, where omega is continuous frequency, okay, or I can say the continuous time frequency. Okay, continuous time frequency, and Z is equals to R e to power, okay, sorry, S is equals to sigma plus j omega, where omega is continuous time frequency and Z equals to R e to power j sigma where sigma is discrete time frequency. So Z is equal to 1 upon 1 minus sigma plus j omega into capital T. Now if we talk about only the imaginary axis, so at imaginary axis of S plane sigma equals to 0, the real part. So Z is equals to 1 upon 1 minus j omega t. So since Z equals to 1 upon 1 minus j omega t, so in the magnitude form this can be written as 1 plus omega square t square, and in the denominator the angle will be minus tan inverse omega t. So in the numerator it will go as plus tan inverse omega t. This is your Z. Now we can see that at omega equal to 0, Z will be equal to a point on Z plane at Z equals to magnitude 1 angle 0 degree. Okay. And at omega equals to infinity, Z will be a point on Z plane at Z equals to 0. Okay. So if you see the mapping, then we can see that omega varying from minus infinity to infinity correspond to locus of points in Z plane is a circle with radius 1 upon 2 in center Z equals to 1 upon 2 as shown below. Okay, so here I have pasted a figure that shows that the whole left half plane is mapped into a circle here. Okay, and thus the imaginary axis, this imaginary axis is mapped into a circle of radius 1 by 2, center 1 by 2. Okay, so this is the mapping. So now a very important point is that, so now we can see that using this, using the difference method to convert analog filter into digital filter, if the analog filter is stable and causal, then digital filter will also be stable and causal. Okay, because whenever any pole is on the left half of the S plane, the system is stable, and this is actually getting mapped into this circle. And in the Z plane, stability is when the pole is inside the unit circle and this circle is inside the unit circle itself, so the digital filter will also be stable. So this is a very important point. Next important point is that since the location of pole, this is very important, since the location of pole in Z plane is confined to smaller frequencies only, because the pole can be inside this unit, this circle only, the circle which has the boundary by purple. Okay, this circle only. And since the location of pole is, for example, P1 is written as magnitude e to power j phase, so we can say that the value of phase can be a smaller value only, because the pole has to lie inside the circle only. So we can say that since the location of pole in Z plane is confined to the smaller frequencies only, thus this method is used for low pass filter and band pass filters only. This is not useful for high pass filter or band reject filter. So these two are very important points. In any competitive exam, they can directly ask you such kind of statements. Okay, so let's move on to another part of this method one. So there is one more method. So in the previous method we have seen backward difference method. So now we will see the forward difference method. So what is this? So here dy t by dt at t equal to nt is written as yn plus 1 n plus 1 capital T minus ynt divided by t. So as we have written in the previous section also, so yn plus 1 minus yn. Okay, okay, so now we can say that S is written as z minus 1 divided by capital T. Okay, so this is the transformation formula, or I can say that z is equals to 1 plus st. Now if I do the mapping, if I do the mapping of imaginary axis of S plane into Z plane, so what will be happen? So at imaginary axis we have S is equals to sigma plus j omega and sigma is equals to 0. So in the Z plane it will be 1 plus j omega t, and since omega goes from minus infinity to infinity, so Z is equals to 1 plus j omega t. Now this can be seen as a, so Z equals to 1 plus j omega t, so we can say that the real part of Z is 1 and imaginary part of Z is j omega t. So the mapping of imaginary axis of the S plane is into a straight line on the z plane like this. Now since we know that the mapping should be such that the mapping should be such that stable analog filter should give us stable digital filter, and we can see that here it is not happening because an imaginary part is j omega capital T. Now we can easily see that the mapping of this green region, that is left half of S plane, will be into this region of the Z plane. Okay, and we can easily see that this whole green part is stable for the analog filter, but this red part or the red region where this is mapping taking place is not stable for the digital filters. It is stable only inside the unit circle. Thus we can say that this kind of transformation, that is the forward difference method, will not ensure that the stable analog filter will lead to a stable digital filter. So that's why this kind of transformation is not good, and that's why this kind of transformation is not used in the computations. Okay, now let's solve one or two examples. And since the forward difference method is not good, so it's not used, we will always use backward difference method. So question is, analog filter transfer function is given 2 upon s plus 3. We have to convert into digital filter using the backward difference method. So we know that HAS, or we can say that HZ equals to HAS, where S is equals to 1 minus Z inverse divided by capital T. So HZ is equal to 2 upon 1 minus Z inverse divided by capital T plus 3. So we can solve this and get 2 capital T upon 1 minus Z inverse plus 3T. Okay. Now generally in the question capital T will be given to us and we can easily find HZ expression from here. Okay. So similarly we can easily solve the questions. There are no issues. The only thing is that we have to replace S by 1 minus Z inverse divided by capital T, and capital T will be given to us in the question. So there is nothing much in such questions. You can easily solve them. Okay, so we have done method 1, that is backward difference method. We have already also talked about the forward difference method. That is not very good and it's not used. Okay, so thank you guys. So keep subscribing the channel, and keep sharing the lectures, and also keep giving us the feedback. So thank you.